Welcome to ACS Webinars, bringing you the best and brightest minds in chemistry, live every Thursday at 2 p.m. Eastern. To view our upcoming schedule, please visit acs.org/acswebinars.
Good afternoon, everyone. For a late winter treat, we have Marc Hillmyer as our presenter this afternoon. As chemists, we largely have an underlying appreciation for the importance of bio-based polymers. Professor Hillmyer's research begins from this appreciation, and it seeks to expand the range and the utility of bio-based polymers to address the really difficult problems of long-term sustainability for our industrialized societies. Marc is a distinguished McKnight University professor and the director of the Center for Sustainable Polymers at the University of Minnesota. His group focuses on design, synthesis, and characterization of new macromolecular materials. As you'll see in his presentation, this includes the design characteristics of industrial utility, renewable feedstocks, and eventual degradation in the environment. So with our thanks to Marc, the floor is now yours.
Thank you very much, Joe. I appreciate the introduction, and I very much appreciate the invitation from the ACS Green Chemistry Institute to share with you research that's coming out of the Center for Sustainable Polymers. So welcome, everybody. It is cold here in Minnesota, minus 12 degrees Celsius. Usually sounds colder than the Fahrenheit temperature, so I hope you are warm and without snow where you are. I'm going to tell you today about a story that came out of the Center for Sustainable Polymers, but I'd like to kind of set the stage by letting you know a few things about the polymer industry that maybe many of you already know. Polymers are produced on the teragram scale. Polymers are the molecules of plastic, and they're produced on huge scale. That's 10 to the 12th gram scale. But as you probably also know, they generate tremendous revenue in the U.S. The U.S. plastics industry creates nearly $400 billion US in annual shipments. So it's a large industry that has a tremendous economic activity. But what you might also recognize is that a large fraction of these materials, nearly all of them, come from finite feedstocks, that is petroleum and natural gas. Moreover, polymers can cause rather devastating environmental consequences if disposed of indiscriminately in the environment. In fact, there's a lot of discussion these days about how much plastic actually ends up in our ocean. Not on purpose, of course, but by virtue of being blown from landfills and things like that. So we're faced with this issue where polymers are very useful. They're produced on huge scale. They result in huge economic activity. But where they come from is finite, and where they go has negative consequences in the environment. And what I'd like to tell you about today is one of our efforts in the Center for Sustainable Polymers to make plastic greener. And we're going to do this, we think, through next generation polymers, and I'll try to describe what I mean by that throughout the talk. In the end, I'm going to tell you a story that was a collaborative story between the folks you see on the slide right now that came out of the center. If you'd like to learn just a little bit more about how important plastics are in everyday society, I encourage you to read this book by Susan Frankel. She wrote a book called Plastic, and I love the subtitle of this book, A Toxic Love Story, meaning that, yeah, actually, we like plastics a lot, but we don't like to admit it sometimes because it can have some negative consequences. But her thesis is that we need plastic, and I agree with that. We need it, and they're not going anywhere anytime soon. And in fact, they're so useful in so many different technologies that they're going to be around for a while. The real question is, can we use them in an intelligent way? Can they be intelligently deployed so that we can avoid these negative environmental consequences? Well, if you go into your house, much like they went into Mark Foster's house about a decade ago, and they took everything out of the house that was made of plastic, you might see a scene similar to this. Now, in an article that was decidedly wrong called The End of Cheap Oil is back, they were talking about all the materials that are made from plastic and where they come from. And I think you'll see many things here that maybe we could do without, like this giant yellow ball we could probably do without. But there are many important things in this picture that are part of everyday life. Why are plastics and the polymer molecules go into them so incredibly useful? On this slide, I try to give some highlights of why you might imagine plastics are so useful in our today's society. Of course, they're lightweight, so for transportation purposes, very beneficial for fuel economy. They can be very protective, so protecting our food from pathogens. They're strong, and especially on a weight basis, some polymeric fibers can be stronger than steel. transparent, very useful in optical applications. You can mold them into pretty much anything you'd like, and they're quite insulating as well. As you can see, this cat is benefiting from the insulating behavior of this polydimethyl siloxane, or this silicone-based polymer here. And I love this picture. This was taken the year before I was born, this Time Life book, and I love this picture because, well, frankly, you just can't take pictures like this anymore. People get upset when you do that. But back then, I guess it was okay. But the two properties that I say would make them most relevant to society is that they're disposable. This used to be a big selling benefit of plastic, because you can throw them away when you're done with them. But that turns out to have some serious consequences, which we'll talk about. But more importantly, they're inexpensive. They can be produced economically. And so for traditional materials, plastic films are often a higher performing and cheaper alternative. But we're faced with this dilemma of where plastics come from and where they go, or where they end up. So what could the future polymer industry look like? Could it be that we take biomass, ideally waste or non-nutritive stuff we can't eat, and through bioorganic and inorganic chemistries turn it into monomers? Those are the building blocks for polymers. Both new monomers, ones that I'll tell you about today, and also established monomers, those monomers that have been around for a while but have been traditionally prepared from petroleum and, for example, natural gas. It'll take polymer chemists and material scientists to convert those monomers into sophisticated materials. And what I mean by sophisticated is, while homopolymers or single component plastic materials have tremendous utility, it's in my view that the future will be in materials that have more sophisticated architectures, more sophisticated connectivity of repeat units that allow us to have controlled structures, which ultimately mean controlled properties. What happens at the end of the life of these materials? Well, all stakeholders will play a role in that, and I argue that we really need to think more carefully about sensible end-of-life solutions, whether that be recycling, potentially incineration, or composting, such that we could have a more closed-loop paradigm for the production and disposal of polymers. This is not going to happen without integrated efforts by chemists, chemical engineers, material scientists, and others, but certainly the Center for Sustainable Polymers is an outfit that tries to integrate those disciplines under one heading. You don't have to believe me at being an important and interesting topic. There are many folks who have written plenty of publications on the topic that is the title of this paper, the valorization of biomass, deriving more value from waste. How can we take waste products and get something interesting from them? Well, in this article that was recently published, the basic thesis is that there is a tremendous amount of biomass. We have plenty of biomass, 10 to the 11th, 10 to the 14th grams of material, and can we use that to make useful molecules? Now, this is a figure from that paper where the authors argue that you might be able to take from fermentation, well, actually you can now, from fermentation, and get L-phenylalanine fermentation of biomass. And through an enzymatic transformation, you can get the compound to this olefinic species, followed by a decarboxylation to get to styrene. Now, styrene is the starting material for polystyrene, and probably this would be the world's most expensive way to polystyrene. But the point here really is that this is the type of thing that people are thinking about, and it'll take the hard work of chemists and engineers to make this actually an economically viable process. But here's an example how you might get an aromatic molecule from biomass. So with that backdrop, really the Center for Sustainable Polymers is trying to change this traditional paradigm of non-renewable resource to environmental hazard on its head. How can we use biomass, abundant biomass, for the production of plastic in efficient and economical ways? So the center was established in May of 2009 for the University of Minnesota, and then in September 2011 we were awarded a Center for Chemical Innovation from the National Science Foundation, which we were just upgraded from a Phase 1 to a Phase 2 center in August of 2014. It was during that expansion that we added researchers not only from the University of Minnesota, but also from the University of California, Berkeley, and Cornell, and you can see them here on the right-hand part of the slide. But the point I'd like to make on this is that we actually have scientists that span the range from metabolic engineering all the way through polymer processing. And so it's really this vertical integration of disciplines that I think is very important for the work that we do in the center. Our grand challenge is to discover efficient and precision conversions of renewable raw materials into innovative polymer products that outperform, not equally perform, but outperform the current suite of non-sustainable polymers from performance, meaning mechanical largely, but other types of performance parameters, environmental, and cost. perspectives. And probably the key word in this grand challenge is cost. How do we do what we want to do in an economical way? The center also has integrative elements that are important for running a center of this size. They include center management, innovation, education and professional development, informal science communication, and broadening participation, all of which are critical. But I want to point out that innovation, effective engagement and partnerships with industry is what we really emphasize. And in the center, we've been very fortunate to have the attention and engagement of nearly 36 companies who actually have sustainable polymer products or interest in sustainable polymers for their industries. I've listed them here. The ones in the green box actually are on our industrial advisory board, which we established when we became a Phase 2 Center for Chemical Innovation. The center really focuses on next generation feedstocks, how to turn those feedstocks into new monomers, how to take those monomers and do controlled polymerizations to generate polymers that I call hybrid polymer structures. That's a thrust where we try to build polymer structures that are not typical homopolymer structures. In this case, I've drawn a block polymer as a key area of interest for the center. So really integrating these three thrusts within the center is critical to our success. Let me tell you about probably the most successful bio-renewable, bio-based polymer out there. This polymer was actually developed at Cargill originally here in Minnesota and now is under the name NatureWorks. This is called Polylactide. Probably many of you heard of Polylactide. For those of you who haven't, this is an aliphatic polyester that comes from sugar. Ultimately, corn is fermented to give lactic acid. The dehydration of lactic acid gives lactide, this cyclic dimer right here. And through a ring opening polymerization, you can generate this aliphatic polyester. What's interesting about this polyester is it's used for so many things, both disposable and durable goods, and it behaves not unlike polystyrene from a materials property standpoint. However, it can be 100% composted in about 45 days. It can be incinerated with low residue. It can be both chemically and mechanically recycled. And its cost is actually comparable to polystyrene and polyethylene terephthalate. It does have some limitations. It's not the toughest polymer you'll find out there. And there are some thermal limitations with respect to its softening point or glass transition temperatures around 60 degrees Celsius. What's amazing about this material is now it's being produced on nearly 1 billion kilograms per year, and most market forecasts that I've read predict 20% annual growth rate in bioplast like this one. So PLA is an amazing material that has found its way into many products, and it comes from biomass, and it can be degraded in a compost completely back to CO2 and water. So a very interesting polymer, but not without some limitations in its properties. And this is where we took on the challenge of how can we improve the properties of PLA in an economical way. And the class of molecules that we were most interested in are called block polymers. And a block polymer is when you tie the tails of polymers together in a single macromolecular unit. So in this case, we have a high glass transition temperature red polymer that flanks a low glass transition temperature blue polymer in this ABA architecture. These are called thermoplastic elastomers, and they really marry the properties of elastomers, rubber band-like materials, with plastics, polystyrene-like materials. That's the classic thermoplastic elastomer, is a polystyrene, polyisoprene, polystyrene. They're used in things like adhesives and modifying asphalt and things like that. And the global market is more than 1.5 billion kilograms. Moreover, they're quite interesting because they can self-assemble into nanostructures like I've shown in this AFM image, but it is this microphase separation that lends itself to these amazing properties of these thermoplastic elastomers. That is, they can be processed like plastics, but they behave like cross-linked elastomers. We looked into trying to look at modified ways to make thermoplastic elastomers, and this is just a recent example from our work where we showed that you can actually take terpenes, beta-pinene, and beta-pinene can be converted into alpha-methylmethylstyrene or a molecule called myrcene. This is a substituted styrene, and this is a substituted isoprene. It turns out those molecules can be polymerized by anionic polymerization to generate this red-blue-red triblock, also a thermoplastic elastomer, but derived entirely from turpentine. Now, the nice thing about this is it behaves not unlike those materials I just showed you, but it turns out these two extra methyl groups on the styrene lend itself to having a higher glass transition temperature than polystyrene itself. So actually, this has much more thermal resistance than the typical craton materials that I showed you earlier. This is a way that sustainable polymers can actually enhance the property profiles of these types of materials. Bill Tolman and I spent many a year working on this polymer, which is also a block polymer of orange, green, orange in this case. But now we've put polylactide at the ends, this bio-based thermoplastic PLA. PLA is a high glass transition temperature material, but what we did is we put something called polymenthide in the middle. Now polymenthide has two interesting characteristics. It comes from menthol, the natural product menthol, and it can be turned into an aliphatic polyester that is hydrolytically degradable. So now I've got a thermoplastic elastomer that comes all from biomass, and it's entirely hydrolytically degradable. I can break these ester bonds just through the action of hydrolysis. This too behaved like a thermoplastic elastomer, mimicking those materials made from styrene, isoprene, and styrene. However, I must say that this was an expensive tri-block, and I always joke that my group is very good at making expensive polymers nobody's that interested in. But making those expensive polymers was really important for us to understand how to synthesize them and understand the thermodynamics, understand their self-assembly, ultimately their degradation characteristics and mechanical performance. It was that backdrop that we really moved to the story that I want to finish up with today. Now I want to tell you about a molecule that was developed in the Center for Sustainable Polymers that has allowed us to make these ABA tri-block polymers in a very efficient and economical way. This molecule is called Betamethyl valerolactone. It's a molecule that's been around actually for a long time. You can see all the attributes here. It's been prepared in this journal called Organic Synthesis, which is a really well-vetted synthetic procedures. It's the spicy apple sweet flavor in Turkish tobacco, so mystery solved there. And actually, it's been used extensively in the literature as a synthon, but very little in the literature on polymers. There are a few patents on putting it in polyurethanes, polymers of this in polyurethanes, but only one paper we could find in the open literature about how to put this into a polymer. Now, why am I interested in this molecule? Well, it also is a cyclic ester, not unlike lactide or menthide. It has this ester unit in this six-membered ring. It has this one methyl group. It turns out to be very important for generating a low glass transition temperature polymer. But what my colleague Kachun Zhang saw was actually this molecule, beta-methyl delta valerolactone, can come from mevalonate. And Kachun knew a lot about the mevalonate pathway in microorganisms, and what he did was using these, I would say, strategies listed over here, he was able to feed a microorganism glucose and generate in the organism beta-methyl delta valerolactone. In fact, the titer of this was about 0.5 gram per liter, so it wasn't that high, but what he did do is he's able to generate mevalonate at nearly 88 or nearly 90 grams per liter, and a simple dehydration and hydrogenation of that molecule gets beta-methyl valerolactone. So in a semisynthesis that incorporated this metabolic pathway and chemical synthesis, we were able to generate this molecule in very high yield and very high purity. Debbie Schneiderman in my group ended up taking beta-methyl valerolactone, and with this organocatalyst triazobicyclodecene, we were able to polymerize the molecule to give this polymer, an aliphatic polyester, with one methyl group here. We studied the kinetics of the polymerization, and we studied the thermodynamics of the polymerization to understand the driving force for getting this polymer and how fast you could get it. And the bottom line is that you can get over 90% conversion within a few hours using a very small amount of catalyst. In fact, we do this in the bulk. We don't use any solvent at all, so this is very conducive to large-scale processing. That's the blue block that would go in the middle of the block polymer. It turns out to have a very low glass transition temperature, which I'll show you in a minute. But what we can do with that blue block is grow off of the ends lactide, and that lactide then can be put onto the ends in this ABA tri-block copolymer format. That's the exact type of architecture that I showed you in the Kraton materials. And in addition, we were able to do that quite efficiently. Now we've got an all biorenewable tri-block with glassy polylactide end blocks with glass transition temperature of 60 and a rubbery low glass transition temperature mid block. They're all from biomass. They're all hydrolytically degradable. And do they perform like normal Kratons? Well, before we look at the performance, let me just prove to you molecularly that we have this. We look at the size exclusion chromatography that tells us how well we were at blocking efficiency to make sure we had that tri-block architecture. We use carbon-13 NMR spectroscopy to understand about the fidelity of the polymerization, that is, how pure each of the blocks are and how we avoided transesterification between blocks. And then the differential scanning calorimetry tells us that the mid block, in fact, yes, does have a very low glass transition temperature, where the PLA block has a higher glass transition temperature. In this case, a little less than 50, but you can make semi-crystalline variants that lead to crystalline PLA that melt well over 140 degrees Celsius. So there's no question that we were able to make these tri-blocks, and they're well characterized molecularly. They also self-organize into these nanostructures that I showed you before, so they act and behave like normal block polymers. But probably most importantly is that from a mechanical performance standpoint, they behave just like the materials that I told you that came from petroleum, the styrene, isoprene, styrene ones. So for example, if you look at this polymer right here, this is a stress strain curve. How much stress do you have to apply to a tensile bar like this over here to get a certain amount of strain given in percent of its original length? It takes more and more stress to elongate the material, but it doesn't break until it's been elongated over 1,600% of its original length. Probably more importantly is the stress at which it breaks is over 25 megapascals, making this certainly quite competitive with its commercial petroleum-based analogs. Now, what I love about this polymer is that not only was it the highest performing aliphatic polyester block that we've ever made, it was by far the cheapest. And in fact, Kuchun showed, this is Kuchun showing that you can actually scale this polymerization up. Actually, it was a year ago today. Oh, that's great. It was a year ago today. We scaled this up to 500 liters, and that certainly caught the attention of industry, who I think recognized that this could be a serious player, because the cost analysis of this actually puts the monomer at around $2 a kilogram, and we showed we were able to get high titers of mevalonate in this 500-liter fermentation system. And so really that block polymer right now, we're interested in trying to translate that technology into real products. And I think that story highlights this idea of connecting next-generation feedstocks, controlled polymerizations, and hybrid polymer structures. We published this work last year at PNAS, and a little story was written up in C&E News on this polymer. At the center is more than just the work that came from my colleagues Frank Bates and Kuchun Zhang in this paper I described to you. Recently, work from Jeff Coates on making new polymer stereocomplexes from renewable resources. In this case, polypropylene succinate makes an interesting stereocomplex crystallite. This was also written up in C&E News. And this melting point over 100 degrees is a very nice feature of this. And I like this quote. It says, with biodegradation, renewable raw materials, and demands placed on modern plastics is what makes this so relevant. Moreover, my colleague Bill Tolman here in the Department of Chemistry at the University of Minnesota has been very interested on the monomer side, but more from the chemical catalysis viewpoint, is how to take abundant carboxylic acids that can be generated from biomass and turn them into monomers, in particular olefins that can be polymerized. Just like I said with styrene from biomass through fermentation processes, Bill's very interested in the organometallic chemistry that can lead to this dehydrative decarbonylation. And that just came out earlier this year. And what will come out, you'll see very soon, is our work on using isosorbide as a starting material for sustainable polymers. And this is work with Teresa Reinecke, where we took a isosorbide, which comes from the hydrogenation and dehydration of glucose, and put an acetate on one side and a methacrylate on the other. And the great thing about this is we can polymerize with controlled radical polymerization now, and we end up making a material that has a glass transition temperature that's about 130 degrees Celsius. So that hopefully will address some of these thermal limitations that can be evident in other sustainable materials.
Great, thank you. There are a lot of questions coming in. I'd like to begin, Mark, with one from Erwin Roosley, who's asking, have you actually done a full economic analysis of this, including water utilization, energy utilization, the full life cycle analysis? And please discuss that with us.
That's an excellent question. There's no question that full life cycle analysis from beginning to end on any new material is critical to actually qualify and hopefully quantify the entire economic impact from cradle to grave, or sometimes people say from cradle to gate out the door of the company. For PLA, that's this 100 million kilogram a year polymer. That has been done actually several times and analyzed and reanalyzed, and you can find that kind of on the website of the manufacturer. In the case of this polymer that we're just developing now, really we're focused largely on our economic analysis in that PNAS paper was focused largely on how much could you produce the monomer for from simply the input and estimated unit operations cost. But when you take that material, and hopefully when we translate that technology into an application where you would then process it into a part and how that part gets disposed and all that, then of course it's going to be critically important to have that full life cycle analysis. And I would say that's where our industrial partners play a big role. They're very good at that, and there's expertise in universities as well. But I think that comes at a little bit later stage, in my opinion, comes at a little bit later stage. But I certainly appreciate the point from all the inputs that are required to start from sugar and end up with a real product.
All right, now a question that's a little more technical. What's your perspective on optimum glass transition points for these renewable plastics?
They have to perform in Arizona and Minnesota. And so the idea here really is that you really like glass transition temperatures. In the case of the block polymers, which remember are hard block, soft block, hard block, you really would like the hard block glass transition temperature to be over 100 degrees Celsius. That's kind of the general rule of thumb there. But there are applications where higher than 100 degrees Celsius, for example, in adhesives that have to perform in high temperature environments, you really would like them maybe higher around the 150 degrees Celsius. For the glass transition temperature of the soft block in the middle, you want to keep it soft and flowing, if you will, or I would say pliable, down to temperatures that are well below any ambient temperature that they might encounter. So I just told you in Minneapolis it was minus 12 this morning. Certainly you would want a thermoplastic elastomer to behave like an elastomer outside Minnesota. You would want the glass transition temperature to be well below that. In the case for this polybetamethyl valerolactone, the TG is around minus 50 degrees Celsius. For polyisoprene it can be minus 60, and for other polymers it can be even lower. So I think a rule of thumb is less than minus 50 for the low block and more than 100 degrees Celsius for the high TG block.
Okay, now a question from Todd Zahn, who wants to ask, what's the time frame here that you see in terms of these renewable plastics becoming truly commercially acceptable and beginning to very substantially replace petroleum-based polymers?
You know, in PLA, which is, like I said, probably the most prevalent bio-based, all bio-based thermoplastic, it's making inroads everywhere. Certainly on my campus and other campuses across the nation, PLA is an important material for food packaging and disposable ware, and it's growing. It has grown over the years from tens of millions of kilograms to hundreds, maybe even billions of kilograms. What basically limits it is cost. And if you go to the store and you want to buy a plastic cup for your party and you're faced with the choice of the environmentally friendly PLA cup and the maybe less environmentally friendly polystyrene cup that comes from oil and does not degrade the environment, which one will you choose? And most people tell me, and many market studies say, you'll choose the cheaper one. And it's really this idea, and I like to say sometimes in the center, we want to trick people into buying the environmentally friendly one by making it the low-cost alternative. And once that happens, I think that it'll be the natural choice for many plastics, especially in packaging and disposable cutlery and foodware, because it'll make economic and environmental sense. And when that happens, I think that's when they'll really start to take over. Of course, it's always relative cost. So when gas and oil are cheap, at least economically, but also there are other costs of gas and oil, it can be more difficult. So it's really this relative cost that matters. What I'll make the argument for, though, is that it's not going to happen just kind of organically. It's the basic research foundations that I talked about today that I hope will then set the stage for innovation in this space that also comes in an economic fashion.
Great. Joel Balbion wants you to discuss a little bit the full range of advantages in terms of environmental degradation that bio-based polymers have over petroleum-based alternatives.
Make one clarification that can oftentimes be misconstrued is that not all petroleum-based polymers are non-degradable, and not all bio-based polymers are degradable. Polymers are degradable based on their macromolecular chemistry, and certainly you can make non-degradable polymers from biomass. I just told you how to make polystyrene from biomass. And you can make degradable polymers like caprolactone from petroleum. I think the big advantage for polymers that are designed for sensible end-of-life solutions is that if discarded indiscriminately in the environment, that there is a pathway to degradation that is more on the scale of months or maybe years and not decades or centuries. And so I think, for example, hydrolysis, oxidative degradation, photochemical degradation, these are all things that can be incorporated into next generation polymers that can help the negative environmental consequence of polymers that do not degrade when disposed of in the environment. Moreover, I think that people are thinking harder about incineration and recycling as really in the infrastructure that surrounds that. So making polymers from biomass that are easily recycled, maybe both mechanically, but maybe chemically as well, getting back to the monomeric starting materials, or that can be incinerated in environmentally friendly ways, that is with low toxic effluent, are important research areas gaining more and more attention.
Dario Bassini's got an interesting question. Can you comment and discuss a bit about bacterial polymers such as polyhydroxyalkanoates and derivatives of gamma PGA?
Yeah, so polyhydroxyalkanoates are typically synthesized in bacteria. The bacteria harvest and store this material, and then you can remove that material and isolate it and make renewable, sustainable, and degradable plastics out of that. Those materials have had a little bit of a struggle getting from conception to market penetration. Again, that is not by virtue of the kind of big picture of biomass to plastic. I think that is all very well and good. It's a matter of doing it economically. And so we have to think about actually how do you get from those starting materials, the feedstock that you feed the bacteria, but more importantly, maybe how do I extract that plastic from the bacteria to ultimately get it in a way that can be processed. And each of those unit operations has a cost associated with it. And so I think that's why it's important in the center that we bring together the metabolic engineers with the polymer processors who can understand how to optimize both of those things. So while PHAs are quite interesting materials, I think that the material has faced challenges with respect to market penetration because of these costs. So I think one of the things in the center is we always try to think about, okay, let's walk this through and see actually how you would make the material on large scale. Let's think about it, and let's design materials that can be done in an economic fashion.
I'm combining a couple of questions here together, asking for a bit of discussion about how you can design to speed up or slow down the biodegradation of PLA.
We just published a paper, and many people have looked in this area, about copolymerizations with lactide that lead to weak linkages in the backbone, linkages that are more hydrolytically sensitive than the aliphatic polyester that's in PLA. Because PLA typically gets assimilated in a compost environment by first hydrolysis of the macromolecule down to smaller molecules that ultimately can be processed by the microorganisms in a compost. So facilitating that initial breakdown by putting in hydrolytically more sensitive linkages through a copolymerization strategy, that is polymerized lactide with some other monomer that has weak linkages. We focused on the acetal linkage recently to do that, but others focus on different kinds of strategies to speed it up. To slow it down, you can also think about copolymerizations, and we've worked a little bit on this in the story I told you about polymethylide. That's an aliphatic polyester, but it has a much more hydrocarbon content, so it's a much more hydrophobic material. So having a more hydrophobic material actually limits and mitigates the amount of water absorption in the material, which will then slow down that rate of hydrolysis. Moreover, people in the PLA field are certainly keen on making highly crystalline PLA, which slows down the hydrolysis, and even something called a stereocomplex, which I mentioned in Jeff's work, a stereocomplex that can have a very high melting point and can also be beneficial from the standpoint of a slowing hydrolysis.
Fengwan Yan wants to ask a bit about the processability of these polymers with respect to using them for extrusions and forming textiles and the like.
That's a really important point. When you take these polymers, and in particular aliphatic polyesters that we focused our attention on, you have to get them from the beaker ultimately to a product, and that does take processes that in the polymer industry are largely melt, non-solvent based processes, which means then you have to heat above that highest melting or glass transition temperature and be able to, for example, extrude them or injection mold them. Now, That puts a limitation on an upper temperature limit. So if your glass transition temperature starts to creep up towards your degradation temperature, that can provide challenges from actually processing the material. Something we definitely think about, something we're concerned with in the case of these block polymers that I told you about with polylactide and polybetamethyl valerolactone, they will ultimately degrade at high enough temperature. And so there are limitations on the extrusion process that are going to be important. Along those lines, people certainly put in additives to polymers that can help prevent or slow degradation during the processing. And I think for different classes of polymers, you may have to develop new benign additives that can help you enhance the processability of the materials. But again, it's a key point that the integration of the center tries to bring. We're worried about that. We made these bars that I showed you about by compression molding, and when we look at the bars before and after the compression molding, we can evaluate how much they've degraded, and in fact, at moderate temperatures, they retain their molecular characteristics very well.
Graham Douglas wants you to speak about any toxicity issues that can be associated with polylactide and its copolymers.
Well, polylactide, and in particular lactide glycolide copolymers, a whole range of them have been approved in medical devices. So, for example, I know bone screws made out of polylactide, which actually implant and they ultimately hydrolyze in the body to lactic acid. And lactic acid is a natural metabolite, so it can be processed. Likewise with glycolic acid and even polycaprolactones. And so certainly in the case of PLA, you can imagine a variety of biomedical applications. When you get a new aliphatic polyester, of course you have to vet that. You have to understand its toxicity. You have to understand how its degradation products are handled, for example, in the body for a biomedical application. And in fact, the materials I told you about, some of those studies are already underway. I can tell you that we appreciate this, and from the standpoint of the monomer itself, we have some preliminary data that says, in fact, it has very low toxicity to microorganisms. We haven't done much in vivo testing. That comes later, but we're happy with initial performance parameters that we've got in that area.
Are there other attractive feedstocks that you can speak to for a bit of short discussion that are alternatives to what you've presented here?
You know, we've been using, in this particular example, sugar because metabolic pathways in these microorganisms that live on sugar is probably the most straightforward thing to do for the metabolic engineer. But I think really we need to focus our attention on non-nutritive and waste biomass, stuff that we can't eat, stuff that we throw away now or burn, and try to get the chemicals out of that using the modern tools of organic and inorganic and organometallic chemistry to get feedstocks that are interesting. So on that standpoint, I would say certainly seed oils, although we can eat those, they can be abundant and are used for industrial applications. Cellulose, more of the corn husk instead of the corn kernels. And I really am fascinated by terpenes, as others are. Terpenes can be produced very economically, and like I said in this alpha-methyl-methylstyrene and myrcene case, can be catalytically converted into molecules of interest. Another molecule my colleague Jeff Coates is very interested in is carbon dioxide, an abundant molecule that is hard to activate but can be done using proper catalytic routes. And so to make polycarbonates and other materials from carbon dioxide is something I think is very attractive and actually is the basis of a company that was co-founded by Professor Coates called Novomer. So there are a lot of other things out there. I think that there are certainly alternatives, including lignin, which is another one I think that has certainly a great deal of interest because of the aromatic nature of the molecules in lignin. How to extract molecules from that allow you to make new bio-based feedstocks.
Well, we're getting close. We probably have time for maybe 2 more questions. One of them is that the audience actually would like to hear a little more about that 500-liter polymerization that we were seeing that overhead for. Can you discuss a little bit about what's the throughput, what's the volume efficiency in that 500 liters? How do you isolate the product, and how much do you obtain?
Yeah, this is not my principal area of expertise. I will tell you that it's a batch reactor, and I know it's quite important to control the oxygen content, the sugar content, and things like this to keep the bugs happy. And that was our first run at that scale. And what we did at the end is we just saved the fermentation broth. We did not take it at this stage to the next step of what I want to say the unit operations to get to the monomer itself. But I will tell you, my students have scooped out of that fermentation broth, added sulfuric acid, and done the dehydration and then extracted the anhydrovalerolactone from that broth. I think this is really where we need partnerships with industry. We need folks who are specialists and experts at the processing of fermentation products to really help guide us down the path of the unit operations that take us from that batch fermentation process to one that can be potentially done continuously and potentially be able to extract that molecule with high efficiency. Those are our next steps, and I think really that's where these partnerships with industry will play a key role.
Okay, this is probably the last question that we have time for. This one's from Randy Waymeyer. Is there any inherent flame retardant activity in PLA or of phosphates or other additives used to add flame retardant properties?
I have to say it's not something I know a lot about. Certainly I would tell you that when it comes to the role of additives, and many polymer products have additives in them, I talked about stabilizing additives from the standpoint of processing. The main thing that you have to be concerned with is, of course, the toxicity and other negative attributes of having an additive. And so people are very interested in using the tools of green chemistry to make fire retardants that are less toxic than maybe the traditional ones. I'm sorry, I don't know the answer in PLA. I'm sure that there's literature on that about how folks have tried to make blends of mixtures of PLA with other things that help retard its flammability. And that would certainly be one of those examples where you could expand the application base of PLA if you were able to do that effectively.
Well, there are a lot of questions that we're not going to be able to get to today, as we thank the audience for them. But what I'd like to do now is to ask you, Marc, for a few final high-level thoughts about how this contributes to global sustainability and the full strategic impact of the message that you're giving to us today.
Absolutely. What we're doing in the Center for Sustainable Polymers is we are laying the basic research foundations for the future polymer industry. I think that given the environmental concerns of where polymers come from and where they go, this really is the future. This is what will be the next generation of plastics that we use. It's not going to happen without the basic research foundations, because what those do is they set the stage for building a polymer industry that can make these alternative plastics in an economical way. And frankly, it's not going to happen if it isn't done economically. And so that's what we're always driving for in the center. We're keeping our eyes on how to do things with simple molecules made in simple ways, using what we understand from the chemistry that we had done, maybe on more expensive molecules. You know, before I started the webinar, there were some questions that came in electronically, and one of them was, how can we convert renewable raw materials into innovative polymer products? I think I gave you an example, and I think the word innovative is key here, because for it to be innovative, we firmly believe in the center that we need to translate what we've done into real products. And I think that right now that's where our attention is certainly how do we take these materials I've told you about, and then through partnerships, how do we now convert those into real products that can bring benefit to society? And I think that's really the driving underlying principles of Centers for Chemical Innovation from the National Science Foundation, of which the Center for Sustainable Polymers is one.
Thank you for watching this presentation. ACS Webinars is provided as a service of the American Chemical Society as your chemistry source for live weekly discussions and presentations that connect you with subject matter experts and global thought leaders concerning today's relevant professional issues in the chemical sciences, management, and business.